Would you join me in welcoming Paul Mackerras, please?
Hi, I'm going to talk this afternoon about some more details, some more lower level details of how Microwatt works, in the hope that some of you might find this all interesting enough and feel that this is an introduction that lets you get into it and actually start hacking on it. So Anton's talked about a lot of this already. Started as a demo or proof of concept for the announcement of the power instruction set architecture being made open last August. So Anton actually pretty much single-handedly, I think, put this together as the proof of concept that actually worked, actually executed basically the entire integer user space instruction set of part of the instruction set architecture. Still quite incomplete, there's still a lot to be done. But the thing is that it's currently, I think, under 10,000 lines of VHDL. So 10,000 lines is a size, I mean, like the original Unix version 6 was 10,000 lines, and that was a size that could be taught in a course and someone could read through it and actually understand everything that was going on. So it's not this enormous pile of stuff that you can never get into. It's something that a good person can reasonably expect to actually understand every part of it. As Anton said, it's all open source, hosted on GitHub, and uses the GitHub methodology of pull requests, so that you have a clone of the repository on GitHub, and you make your clone, you push your changes to your clone, and then you do a pull request for Anton, and he in his wisdom decides to pull or not. As he said, we're mostly targeting simulation and FPGAs, and we're using Wishbone for the memory interface. Wishbone is a kind of thing that's out there that is pretty simple. It's just based on using multiplexers rather than like a tri-state bus like we might have used in the old days. I'll just talk briefly about what the Power ISA is like. It's a 64-bit RISC architecture, RISC in the sense that it has fixed length instructions of 32 bits, and the only instructions that access memory are the load and store instructions. So there's no like add two values and store the result in memory in one instruction like you would get on x86 or a System 390 or 68,000 or those kind of architectures. It's not reduced. I mean, people sometimes say reduced instruction set computing, therefore it must be a small instruction set. That's not that at all. It's not a particularly small instruction set. We do have lots of registers. In the architecture, there's 32 general purpose registers, 64 128-bit vector scalar registers. This is kind of a unification of the floating point registers and the vector registers, which we used to have. We used to have 32 64-bit floating point registers and 32 128-bit vector registers, and then in Power 7 timeframe, the architects added another 32 by 64-bit block and then said, okay, this makes a rectangle, which is our vector scalar registers. Then there are the special purpose registers. There's a 10-bit space, so up to 1024, but not all the space is occupied. The important ones for user space code are the link register, used for procedure calls, the count register, which is used for indirect calls and for decrement and branch type loops, and the integer exception register, which has got some carry and overflow type bits in it. And then separately, there's this 32-bit condition register, which stores the normal sorts of condition codes that you might expect, except we've got 8 sets. So there are 8 sets of condition codes that you can set with compare instructions, and then you can do, operations between them, and you can do branches based on that. And there's the machine status register, which stores things like privilege flags. So that is one that we haven't implemented yet, but if we want to do a supervisor mode, then we need an MSR because it's got the bit in it that says whether you're supervisor or user mode. Our instructions have between 0 and 3 register operands. So an example of a zero operand instruction might be the synchronized instruction, which is a memory barrier and essentially tells the CPU to stop and wait for all the previous instructions to finish before it goes on with the next thing. One with 3 operands could be, for instance, a store with indexed mode addressing. So you've got one register that gives you the data to be stored and 2 registers which get added together to give you the address to store to. And we have 2 addressing modes, register plus constant and register plus register. The constant in the first mode comes from the instruction. It's a 16-bit field in the instruction. Okay, so then just looking at the overall structure of the pipeline, this is similar to the diagram that Anton put up before. Fairly straightforward pipeline. We have fetch 1, the iCache, so then fetch 1 generates an address, the iCache gets the instruction and passes that down. Decode 1 and decode 2 work out what the instruction is doing. Decode 2 reads stuff from the register files and passes that down to either load store 1 or execute. Anton's diagram had multiply and divide sort of parallel to execute, but we've actually kind of moved them inside execute, or at least we have in my branch. Haven't merged yet. But that's the plan. Load store 1 goes down to the dcache. You end up getting a result which goes back to write back, which goes back into the register file and the condition register file. Write back sends the signal back to decode 2 to say that we're complete, because it can take a variable number of cycles to get through execute or load store. Then I've drawn lines in blue which are stall. That means that a pipeline stage can't do what it needs to do in this cycle, and it needs the previous stage to stop and not give it anything new so it can continue. These stages are each effectively 1 clock cycle. You can think of a thing moving, an instruction moving down 1 step on each clock cycle in general, although in some cases things take more than 1 clock cycle. And there's a flush line that I've drawn in red, and what that is when a branch gets to execute 1, we use this pathway from execute 1 back to fetch 1 to send the new address that we need to branch to. And at the same time, we send out this flush signal to tell the earlier stages of the pipeline, forget what you're doing. We're not executing that instruction because it comes after a branch that we're taking. So just forget what you're doing. And then that address goes up to fetch 1, and then we start fetching from that branch target instruction. So it's pretty straightforward. The stall signal tends to be a combinatorial signal in that when you get a stall at execute 1, that's got to propagate all the way back up to fetch 1 to say stop everything, at least pause everything for a cycle, because I can't take anything new next cycle, so you better not give me anything new. So that goes back up the pipeline to say pause for a cycle until we unblock things down lower. So that's a kind of view from how instructions propagate through the system. It's also interesting to look at this from the point of view of data and how that propagates through it. So what we have here is at the top left we've got our register file. That's a 4-ported RAM. So it's got 3 read ports that read asynchronously. In other words, you just put the address and you get the data in the same cycle. And 1 synchronous write port. In other words, you give it the address and the data, and then on the next clock edge, it actually does the write. So that's fairly wide. In FPGAs, it tends to be implemented as what they call LUT RAM. We generally don't have to worry about that. We just sort of say what we want and the synthesis tools work it out. But I believe in the Xilinx one, it turns into using the LUTs as the storage for this. So we have our 3 register operands which are indexed by these RA, RB, RS are fields of the instruction word. So the specific sets of 5 bits in the instruction word that indicate which are the register numbers you're reading for each of the 3 potential operands. And that register file started out as 32 entries of 64 bits. We've since doubled it to 64 entries, and that means that we can store all of the special purpose registers that we implement in that RAM as well. And it kind of unifies the hazard detection and that kind of thing between the GPRs and these SPRs that we've implemented. Then there's a bypass, the next set of multiplexers. You can see that kind of trapezoidal symbol. Is that trapezoid? Rhombus? Whatever it is. That quadrilateral is a multiplexer which can select the data being written. The data that's going to be written, is, like on the next clock edge, can actually then be bypassed to be used in the current cycle if you're writing the same register that you're reading. So there's that bypass. On the B operand, we can bring in an immediate constant, which is one of several fields of the instruction word, can come in there. And we come down into this set of registers, which are this RD1, RD2, RD3, are the actual operand values that are coming out of the Decode 2 stage. So that is the output of Decode 2, which probably should be called issue, but whatever, it's called Decode 2. So then we've got those 3 operands that go into the various execution units, if you like, the adder, subtractor, the rotator, the logical unit, the multiplier, the divider, and there's a bunch of other things. So when you look in the VHDL, in execute 1, there's this big case statement that says if it's, op add, then result is the output of the adder, and if it's, op rotate, then it's the output of the result, colon equals output of the rotator. And there's just this big case statement. So that big case statement then generates this enormous multiplexer at the bottom, which is taking the answer from whichever functional unit it was that was supposed to generate according to what instruction we're executing, and puts that into this result register, which is the output of execute 1. Now, at the moment, that then goes into write back, which is kind of this stuff on the right, where we select either the output from the execute or the output from the load store thing. These operands go also into the load store unit, and for a load, we get the data back, which then goes through a formatting stage. The formatting stage is that you get 64 bits back, but you only did a load byte of, this, you read this much, but you're only interested in that much, so you've got to shift that to the right and mask off the rest in order to get the value to write into the register. So it's that shifting and either 0 extension or sign extension. And in the future, when we do unaligned loads, it will be also stitching together for an unaligned load, you probably have to, if it's more than 1 byte, you probably have to do 2 8-byte reads and then take a bit of this 8 bytes and a bit of that 8 bytes and sort of rotate them and stick them together. And that's what the formatter does. And so that goes back up into the write data port. So from the point of view of the data, that's how stuff is going around and around in the system. Now, what I want to do, I've been working on but haven't quite got it ready to commit, is then add another bypass from the output of the execute 1 back into the input of execute 1 and load store, so that you see in the previous slide, if you had, let's say, an add instruction that put a value into R5 and then an AND instruction that used the value from R5, so the first one comes through, it gets into the result, but that is then not yet available to be used in the next cycle in execute 1, because we've got, if you look at the loop, we've got 2 flip-flops in the loop. So that means that you do the add instruction and then you've got a stall cycle when you can't do anything because the operand isn't ready yet, and then you can do the AND in the third cycle because you've got to go through these 2 flip-flops. So the minimum time to go around the loop is 2 cycles. With this bypass coming in after that set of RD1, RD2, RD3, we'll be able to do back-to-back integer operations where, an add followed by an and can be done in 2 cycles. Okay, so now looking at the particular stages in order, we start with fetch 1. Basically, all it does is just generate a stream of instruction addresses. So we've got this NIA thing, and left to itself, it would just generate, 100 hex, 104 hex, 108 hex, 10C hex, 110 hex. It just keep on doing this forever. It has the signals coming in, the stall and the redirect. So the stall is going to say, don't give me the next number on the next cycle, just repeat the same number. And the redirect is going to say, start again from this number. So you do a branch to 200 hex, then it's going to spit out 200, 204, 208, and so forth. That goes into the iCache, and as long as we're hitting in the iCache, we can do it in one cycle. We can accept a different NIA each cycle and generate the instruction word on the next cycle. So we can do one CPI, one cycle per instruction, as long as we're hitting in the iCache. If we miss, then there's a state machine that starts up and we send the stall signal back to fetch 1 to say, hang on a minute, and then iCache is going to send out requests to memory to reload the cache line, get the stuff back, then off we go. Fetch 2 basically does pretty much nothing. We could possibly maybe get rid of it, I don't know.
I've tried at this timing and I didn't try hard.
Okay, so essentially what it does at the moment is provide a way to stall iCache. It provides a buffer where, if subsequent stages want to stall, we can do the stall at that level and it doesn't disturb iCache, but we can possibly get rid of it. Decode and issue. So decode, we've got decode 1 and decode 2. As Anton said, we've got the major opcode in the top 6 bits. That's 64 values, obviously. Several of those are opcodes that then have a minor opcode in lower bits, like opcode 31. It's bits 1 to 10 of the instruction, then give you a minor opcode that tells you whether you're doing an add instruction or an and or a synchronize or whatever it is. So we have a decode table for the top 6 bits, and for some of the opcodes, we then have other decode tables for the minor opcode. And that, whether it's whichever table it comes from, we get the same 38 bits of control information that then go down into decode 2. Decode 2 gets a bit more interesting. It's responsible for reading those operands, general purpose registers, condition register, XCR, SPR from the register file, the reg file and the CR file. I talked about that. It also is the place where we detect hazards. So we detect the fact here that the previous instruction wrote a register and this instruction is reading it, so therefore there's a dependency there that we need to be aware of and to manage. Because not all instructions execute in a single cycle, we need to know about that and to stall a previous instruction if it's needing some data that's not yet available. We then go down to load, store, and decache. So the first cycle does address generation and store data formatting. Second cycle, asynchronous read of the cache tag memory and compare. And the third cycle, we either have the data which we then select the right way, or we start the state machine to access memory. So is that not quite right?
How I want it to be. It's not exactly how it is.
Okay.
But sort of.
Sort of? A high-level description, reasonably good? Okay. We can talk to Ben later if you want to know the fine details. Ben wrote all this stuff. Execute. So currently, all of our integer instructions, except for the multiplies and divides, execute in one cycle. The Power ISA has got these interesting instructions that do things like rotate and generate a mask from this bit to that bit and AND the two together, and then AND with, AND a register with the complement of the mask and stick things together and write the result back. All that happens in one cycle. The divider is a bit slower. It takes between 10 and 66 cycles, depending on its operands. The divider was really more about getting it to work without using an enormous amount of resources than making it really, really fast. The multiplier needs work. It currently takes 18 cycles. Part of the problem is that Vivado for the Nexus parts, the Arctic 7, whatever, tends to have warnings that come up because it's got these DSP things in it that have got multipliers, 18 by 14-bit multipliers. And in VHDL, you just write a 64 by 64-bit or 65 by 65-bit multiplier, and then the Vivado tools are then turning that into using a whole pile of DSP things. But then it has this checking stage that says you've got to have a flip-flop on the input and the output of this multiplier and the individual things that it's been broken down into. So we tend to get a lot of warnings out of it. So somebody really needs to have a good look at what the DSP and the Arctic 7 can do and write some custom VHDL for the Arctic 7 and then perhaps for the ECP5 and whatever. It's very unoptimized at this point. There is a proposal to use a 3-stage pipeline for execute in order to match the latency of load store, in order to reduce the effective load to use latency. We would need to then have bypasses from each stage of that 3-cycle execute pipeline. Having 3 cycles might also enable us to optimize some other things. Moving on, there's writeback. So this includes the load data formatting. That's taking the 8 bytes that we get from the decache and rotating it and masking it and sign extending it and also byte reversing it. Power has byte reverse load and store instructions, which basically load or store in the opposite endianness from the processor's natural endianness. So if your processor is naturally little endian, as Microwatt is, then these byte reversed ones do big endian. The CR0 setting for dot form instructions. This is instructions like in the Power ISA, if you say add R0, R1, R2, it'll add R1 and R2 and put it in R0. If you say add dot, with a dot on the end of the instruction, it will do the addition, but also then compare the result with 0 and put a condition code setting in condition register 0 to say whether the result was equal, less than, or greater than 0. So that's done in writeback, and it sends data to the register files. So that's basically how everything fits together. Fairly considerable to-do list. One thing that would be really useful is to get on and do, well, the privilege modes, certainly supervisor mode, because then that means we can run Linux. And then it'd be kind of nice to do the hypervisor mode as well, which would mean that we could then start running KVM on it, which would be kind of cute, because that's what I do. I do KVM. But of course, for that, we also need a memory management unit. We don't have anything at the moment. It's just completely that the effective address generated by the instruction is the address that goes to memory, and it's the address that's used to look up the data cache and the instruction cache and everything. As Anton was saying, perhaps we'll start with a software-loaded TLB. That would be relatively straightforward to do initially. I guess particularly if we had separate ITLB and DTLB. And then, there's all sorts of ideas about, like Ben was saying, have some kind of hidden firmware that implements the radix MMU from like Power 9 does. Power 9 has actually got, the radix MMU is new with Power 9. The previous processors, Power 8 and so forth, simply use the hash page table, which is a fairly complicated structure and has the disadvantage that it's not very cache friendly. when you boil it down, that is the big reason not to use it, is that it doesn't cache very well. So yeah, that's something where there's a lot of room for someone to come in and say, I think we should do this, and write some VHDL and get it going, and would be very much appreciated. We need to implement interrupts as well. So both in the power instruction set architecture, the term interrupt, of course, we do the IBM thing of, we use the same word as everyone else in the industry, but we mean a slightly different thing by it. So an interrupt is the change in control flow due to an event. So both something like a page fault, which is that the program itself did something and it's a synchronous thing where it's a direct result of the execution of the program, that we divert execution flow from the program we were doing to the interrupt handler, and an external interrupt where a device is saying, I've read that block of data for you and it's in memory now and you can go and use it, and it gives us an interrupt. The term covers both cases. We need unaligned loads and stores. We don't do them really. Well, we kind of do them if they fit within an 8-byte chunk of memory. But if they cross between two 8-byte chunks of memory, we don't trap, we just give you the wrong answer. It'd be nice to reduce the load to use latency. We need some kind of floating point, particularly if we want to run a stock Linux kernel. We don't necessarily have to have a complete floating point unit, but we kind of do need the registers. What we want to do is avoid the temptation to create a soft float variant of the ABI. This happened on 32-bit embedded PowerPC, and it was a real pain because, all of a sudden you need different tools, and the one binary won't run here, and will run here but won't run there. We really want to avoid that, and then get Linux running. That would be terrific. So that's that. Any questions? Are we doing the microphone thing?
So you're asking for volunteers to help you write some VHDL to implement some of the missing features or improve some of the features that are there. How would somebody do that and avoid stepping on the patent landmine from other CPU or ISA vendors?
Other CPU vendors?
Yeah, so I think you mentioned there was a patent, some sort of patent deal with the Power9, with the Open Power Foundation. So I'm presuming that you can use.
I mean, there's no patent landmine as far as IBM patents are concerned.
Yes, but so I'm not a CPU expert, so how would I know I wasn't stepping on AMD arms?
I mean, that is a good question. I mean, in general, at least the advice I've been given is not to go looking at patents, because if you can be shown to have looked at a patent and infringed it, then it's willful infringement and triple damages. So, as a means of communication between engineers, patents are completely useless.
Also,
so yeah, go on.
We probably not at a stage where what we do is innovative enough to be an active patent today. I mean, I'm pretty sure, right. But every idea we've been having here have been probably
are more than 20 years old. Yes.
Yeah.
That's a good point.
Curious, you said currently it's a very simple, like 10,000 line implementation for Microwatt and stuff to keep it simple for an educational, someone can come in and actually understand the whole thing. Going forward, is that going to continue to be a goal so someone can get involved? Even if some more complex stuff gets implemented, you could still implement this and understand the lot.
Yeah, it's an interesting balance between, on the one hand, wanting it to be reasonably performant and not use too much resources, but then on the other hand, be easy to read. And that's something we'll have to try and keep in balance as we go forward. It's up to the maintainer, really. Plenty of time? I talked too quick, did I? There's a question there.
When you say you're hoping to implement an MMU, is that something that you would create your own one or try and use an existing design?
Well, at the level of architecture, we would want it to look, or at least made to be able to fake looking like the Power 9 architecture, which is the ISA version 3.0b. That instruction set architecture specification is publicly available, I think, on the openpower.org, openpowerfoundation.org website. You can find the specification, and it's fairly long and complicated, and it talks about in-memory data structures and stuff. Now, that all sounds very complicated, but the saving grace is that there's a paragraph early on that says that the architecture can be implemented by a combination of hardware and software. So it doesn't all have to be in hardware. You can have part of it in software, and you can define implementation-specific interrupts to do software emulation of most of the architecture. There's a subset that has to be done in hardware, which is basically the subset that's used for the early part of interrupt handling. But certainly the MMU is something that can be implemented. You know, you can have the slider between all hardware and all software and put the slider at any reasonable point between them. So we would want someone who's read the architecture and knows kind of what we needed to at least be able to fake looking like.
If somebody's interested in working on the MMU, talk to me first. Also,
I should have mentioned that there is a Slack channel where we discuss things. You can get the address from Anton or possibly Hugh. Do you need an invitation, or is it anyone can join? Open channel, okay.
if we very, very, very much welcome people who have experience dealing with timing in FPGAs.
You also mentioned like the reasons not to use the hash type memory lookup. You use radix tree or something because you have cache coherency problems or something. Is that
not coherent?
Oh, so no cache miss.
It's just latency.
Yeah, it's all latency. Okay,
yeah, it's just
so,
performance and latency.
Oh, so it's cache miss on latency, not on like size or something. Because I'm like, you're using such a small architecture, you're not going to be running out of any. Okay, cool.
The hash page table, I think, would probably be more complex to implement. Yeah, well, because of the SLB, yeah.
This isn't SLB anyways.
No, there's no SLB. But if we did the hash page table, we would need to have an SLB. But we don't particularly want to do the hash page table. Okay. Is that it? Any more?